Hello, everyone. My name is Ming. I'm a principal research scientist and a science lead at the Privacy Technology Group Data 61 Cyro, Australia. So today I'm delighted to give a talk about our work on the impact of deep learning model architecture on its privacy weaknesses. This is a joint work among University Technology Sydney, Data 61 Cyro, and City University of Macau. This is a quick outline of my talk today. First, I would like to discuss the background and the motivation of our work, and then I will explain the methodology and the key findings of our paper. And if we have time, we can explore more experimental results in the paper. So let's get started. So first, a very quick slide on the background. So I would like to talk about the current global AI regulation activities. So we know that the European Union has been working on this first AI Act for a few years now. And this groundbreaking AI regulation is expected to be put into effect in 2026. And last October, President Joe Biden signed off an executive order on the safe, secure, and the trustworthy development of AI. And in January this year, the Australian government also released its response to the consultation for safe and responsible AI. So as you can see here, there is a global effort on AI regulation, and privacy protection is one of the main focal points. So when we talk about privacy risks, so let us do a very quick review on the widely studied privacy attack methods. First one is called the membership inference attack. So here I show a very generic model. On the left-hand side, we have original data, X, usually consisting of two parts, sensitive information, S, and the non-sensitive information, U. In the middle, we have a general block, which shows any AI ML function. On the right-hand side, we have the output observation, Y. Y could be anything, could be data, could be answer to queries, or could be output or parameters from AI ML models. And regarding membership inference tag is basically regarding the probability of guessing whether a sample H belongs to the training data or not, given the observation Y. And here Y refers to the victim model's prediction results or confidence scores. A typical method of membership inference tag usually involves construction of a shadow model and an attack model. Second privacy attack method is attribute inference attack, the same model. But for this one, we are more concerned about the mutual information between the sensitive information S and the observation Y. So in this case, Y refers to the victim model's intermediate features. And a typical method would involve training a tag model based on the said features. So finally, we have a gradient inversion model. Again, same system model. But for this case, we are more interested in the posterior probability of sample X conditioned on the observation Y. So Y refers to victim model's gradients. A typical method would involve the optimization between gradients and the reconstructed samples. So next, let me talk about the motivation of our work. So basically speaking, from the literature, we have observed that privacy attack performance actually varies from model to model, which cannot solely be explained by overfitting. So this makes us think about the following question. Does the design of a model's architecture play a role in its privacy weaknesses? In other words, we are trying to find the answer to the question that whether it is possible that some models are just inherently more privacy vulnerable than the other models. And if it is the case, why? So this is the fundamental question we would like to answer. In order to answer this question, we have developed a methodology. Let me explain it in more detail. So our methodology consists of two parts. So part one, we would like to conduct a head-to-head comparison of convolutional networks and transformers. For convolutional networks, we have studied the ResNet 50 and the ResNet 101. For transformers, we have studied swim T and swim S as the representative models. And in our study, we have evaluated 3 privacy attacks: membership inference attack, MIA, attribute inference attack, AIA, and the gradient inverse attack, GIA. More importantly, we would like to ensure a fair comparison. That means in our experiments, we have used the comparable model sizes, similar overfitting levels, and similar primary task accuracy for both convolutional networks and the transformers. So actually, part 1 is the easy part of our study. So it's just some hard work on the experiments. What we would like to discover is why. So for example, if we find transformers are more vulnerable in terms of privacy than convolutional networks, we would like to understand why. We would like to identify the primary causes. So that gives the part 2 of our methodology. We would like to find a way to morph a convolutional network to a transformer-like network step by step. And we would like to monitor the privacy attack method's performance along the process. In this way, we can identify the steps or the design components that introduce significant privacy risks. So here, let me show the key paper that inspires our work. So in this CVPR paper, 2022, the authors proposed a method to modify or morph a ResNet 50 network to a CovNext T network. CovNext T network is a transformer-like network. This paper contains lots of details regarding how to do the transition or the model morphing. Due to time limitation, we cannot explore the full details. But here, I do want to comment on the intuitions of why we can do this. In other words, I would like to show the connections between convolutional networks and the transformer networks and show that they are not that different. So in order to explain that, I would like to show 3 key features of ResNet or convolutional networks. So first feature is convolution. Mathematically speaking, convolution is very similar to cross-correlation, which can be seen from the mathematical definitions here. The only difference in those 2 definitions is the sign in the filter function, denoted by G tau. So that means if you want to flip your filter, you will get convolution. If you don't flip your filter, that's cross-correlation. As a tool example, I show here that you can achieve the same convolutional results using NumPy convolve function or using NumPy correlate function. As I said before, choice is yours. If you want to flip your filter, you use NumPy convolve function. If you don't want to flip your filter, you just use the original correlation function. In transformers, we also needed to calculate the correlations among tokens. And it has a fancy name, which is called attention. I'm pretty sure most of you have already familiar with this notion. Second feature of ResNet is residual net connections. This is mostly for the mitigation of a gradient vanishing. And in transformers, we have almost the similar thing, the same thing, and but it with a different name. It is usually called a skip connection, but they are basically the same thing. Finally, for ResNet, we have 1-by-1 convolution blocks. This is mainly for dimension reduction or restoration. And in transformers, we have similar things. And this function is realized by multiplex matrix multiplication by the matrices WQ, WK, and WO. So here I just want to show the connections between these 2 seemingly different architectures and comment that they are not that different. So we can do the step-by-step modification. So next, let me quickly show just one example of our experiments. So first, a very quick summary on the settings. This slide is a little bit boring. So we have used various data sets and used standard assumptions for GIA, AIA, and MIA, all standard, nothing fancy. Secondly, we use task accuracy to measure the utility of the victim models. And to control the overfitting level, we used the accuracy difference between the training and the testing of a victim model to make sure both convolutional networks and the transformers are trained according to a similar overfitting level. And to average out the randomness, we conducted around 1.5K experiments, training instances with around 1.2K training hours. Okay, so let me show our main findings, just the 2 bullet points. So first, we have found that transformers exhibit higher vulnerabilities to the studied privacy attacks than convolutional networks. And here is why. We have identified a few primary causes. Basically speaking, transformers tended to have fewer activation layers, and the transformers adopted this petrify methods and the layer normalization. Those are the 3 primary causes that lead to more privacy vulnerability of transformers. So very quickly, just show this one example of results. So as I said before, we did a step-by-step modification or morphing from ResNet 51, the first row, all the way to last row, CovNex, which is a transformer-like model. So you can see there are 14 steps. And for each step, we have an immediate model. And for each immediate model, we test the efficacy of a GIA and show the performance results. Regarding the performance results, we use task accuracy to show the utility. And to show the efficacy of a gradient inversion attacks, we have used standard metrics such as MSE, PSNR, SSIM. And here are the results. As you can see here, if you look at the first row and the last row, you can see the task accuracies are actually quite similar because we make sure the model sizes are quite similar. However, if we look at the efficacy of the GIA, you can see GIA is more effective on transformers, the last row, in terms of MSE, PSNR, SSIM. That means you have a much higher chance to recover the underlying samples when applying the GIA on transformers than on convolutional networks. More importantly, we can see that 3 steps stand out. They are petrify, removing activation, and batch normalization to layer normalization. As you can see here, if you focus on line 4, 10, and 12, you can see the efficacy of a GIA shows a significant jump about those 3 steps. And those are the primary causes that lead to transformers vulnerability in terms of privacy. So let me talk about some intuitions. So first, transformers tend to have fewer activation layers than convolutional layers, and we need to be aware that activation is actually a non-linear operation, which is hard to reverse engineer. So that means transformers tend to preserve more information learned from the training data. Second point, the petrify method is actually a non-overlapping convolution. Basically speaking, you just set the stride to the filter width, you will get the petrify method. And using this method, actually, from this paper, you can see that it is much easier to learn information from the input data. The authors of this ICML paper showed some mathematical proof and more experimental results to support our statement. Finally, regarding the layer normalization layers, we found that parameters in the layers increase the risk of overfitting. And this has been corroborated by this NIPS paper published in 2019. Again, the authors provide more mathematical proofs to support our statement here. So final slide. In conclusion, in this work, we discovered that transformers tend to be more vulnerable to privacy attacks than convolutional networks. More importantly, we have identified several primary causes, such as fewer activation layers, the adoption of a petrify method, and layer normalization. So regarding privacy protection measures, they are quite straightforward. To enhance the transformers in terms of privacy, we might want to insert more activation layers, more non-linearity operation, and introduce additional noise to the identified privacy leakage layers. That's pretty much conclude my presentation. Thank you very much. I would be happy to take any questions or comments.